And today's lesson is 5.3 and 5.5, Triangle Inequalities. I'm going to open with an idea called the exterior angle inequality. And what this tells us is, if you're looking at the measure of an exterior angle of a triangle, it is always greater than the measure of either of the two remote interior angles. So looking at this one specifically, we can see that angle 1 is in the exterior, and angles A and B are its remote interior. What we learned about these in our last unit was if we add the two remote interior, angle A plus angle B would equal angle 1. You add the two remote interior to get the exterior one. What the exterior angle inequality is based on is if it takes angle A plus angle B to equal angle 1, then angle A would have to be smaller than angle 1, and so would angle B. So in other words, the measure of angle 1 would have to be greater than the measure of angle A, and the measure of angle 1 would be greater than the measure of angle B. So basic idea again, any exterior angle of a triangle, such as angle 1, would always be less than the measure of either, or greater than, excuse me, greater than either of its remote interior. So if I were to extend this out, and let's say I call that maybe angle 2, then I could say that the measure of angle 2 is greater than the measure of angle A, and the measure of angle 2 would be greater than the measure of angle C, because A and C would be its two remote interior. So here's an example using this idea. We have a larger triangle with angle 1 and angle 11 being on its exterior, and then within that I have drawn two segments to create three smaller triangles. And on part A, we are going to name all angles less than angle 11. We're going to name all angles less than angle 11. So angle 11 is in the exterior, so we're going to look for any angles that would be considered remote interior. So what I like to do is kind of highlight this, so that way I'm looking at just one of these triangles at a time. So I'm currently looking at the triangle that has interior angles 8, 9, and 10. Angle 11 is formed by extending that side out, so it would be an exterior angle of that triangle. So we would say that angle 11 would have to be greater than both angle 8 and angle 9. We wouldn't count angle 10 because they're supposed to be remote interiors, and angle 10 is adjacent to the 11, which means it is not a remote interior. However, 8 and 9 are, which would guarantee that they're less than angle 11. So that's it for that triangle. If I continue this, and now I'm looking at this section, that whole triangle there, I could add two more to my list. And the two that I could add to my list would be the other remote interiors, which would now be angle 5 from this corner, and angle 6 from the top. And then continuing, if I look at the entire triangle, two more to add. Angle 2 would be remote interior to 11, and so would angle 4. So those would be the 6 that work out. Angle 8, 9, 5, 6, and 2, and 4 would all be less than angle 11. Part B, I want to name all angles greater than angle 7. So all the angles that would be greater than angle 7. So angle 7 is here. It's on the inside. So I would think of it as a remote interior. So to begin with, I'm going to look at this central triangle. Just the one in this region. So there are two exterior angles for that triangle, 9 and 3. However, 9 is not going to count because it's adjacent to 7, which means they're not remote, but angle 3 would be. So angle 3 is remote exterior, so it would be greater. As a reminder why that's true, our rule for finding measures, the measure of angle 7 plus the measure of angle 6 would be equal to the measure of angle 3. So that means 3 is bigger than either 6 or 7. And then the other triangle that has angle 7 in a corner would be this section here. Angle 9 is still exterior, but we're not going to count it because it's right next to 7. But angle 1 is exterior and it's not adjacent to it, so it's the other remote one. So the only other answer we have for this is angle 1. The side inequality theorem gives us a way to figure out how the sides relate to each other if we know how the angles relate to each other and vice versa. So if one side of a triangle is longer than another side, then the angle opposite the longer side is larger than the angle opposite the shorter side. So the key to this is that we're looking for the ones that are opposite. So as an example, on this triangle here, I have that AB is 3, BC is 5. So clearly we could say that AB is less than BC. And then we could, even though we don't know what the measure of these angles are, because 3 is less than 5, I could look at what's opposite of 3. That would be the measure of angle C. Would have to be less than what's opposite of 5, which should be the measure of angle A. Other ways that you can tell that, opposite means they're not adjacent, it's across from. So if this side was AB, well, I've already used that point and I've already used that point. Triangles will only have 3 vertices to pick from. So if AB is here, opposite of it is the only letter that remains, which would be C. Right here we're looking at BC, so then we're going to use the other letter for the angle, which is A. So, in other words, you look for the biggest side, across from that is the biggest angle. And you look for the smallest side, across from that is the smallest angle, and then whichever one was kind of in the middle, that would be across from the middle angle. This also works the other way. If you know the angles, then you can also know the sides. So if one angle of a triangle is larger than another angle, then the side opposite the larger angle is longer than the side opposite the smaller angle. So for this case, I only gave you 2 of the angles. However, we can use a previously learned technique to figure out that third angle. So what we could do is add the 2 we know, the 38 and the 55, which gives me a sum of 93. We know the total of all 3 of them would be 180. So we could do 180 minus the 93 to find out that our angle F is 87 degrees. And then we could list out our angles in order from least to greatest. Measure of angle E is only 38, so that's smallest, which would be less than the one kind of in the middle, would be the measure of angle D, which would be less than our largest angle, is the measure of angle F. So now we know that's 87. We've got those listed out there. Then we can figure out what the sides are by looking at the same order. So angle E was our smallest angle. Across from that, we would have side DF. And also, since this used E, this has to use the other 2 letters, which would be less than. Measure of angle D was the middle one. It's across from EF, which would be less than our largest one would be across from this, which would be DE. So we have written those from least to greatest. So even though at this point we have no idea what those sides actually equal, we know it goes in order from least to greatest, DF, EF, and DE. So example 2, write the measurements of the triangles in order from least to greatest. So essentially just do what we just did on the last example. So try these out on your own. Take a little bit of time to draw each triangle and list them in order from least to greatest. I would probably start with the information we were given. So for part A, I would start with the measure of angle L is less than the measure of angle Q, which is less than the measure of angle B. And then go with the sides that are opposite. Opposite of L is QB, which would be less than, opposite of Q would be BL, which is less than, opposite of B is QL. For our next one, our smallest side is DH, which is less than, the next one will be HL, which is less than, the greatest one is DL. And then look for opposites. Opposite of DH is angle L, which is less than the measure of angle D, which is less than the measure of angle H. And again, how we could tell those, DH was here, opposite of it was L, so put that there. HL being here in the middle, D is opposite of it, and then DL, 8 is opposite of H. Triangle inequality theorem is saying that the sum of the lengths of any two sides of a triangle is greater than the lengths of the third side. The sum of the lengths of any two sides of a triangle is greater than the length of the third side. So if I want to create a triangle, I do have some qualifications that I have to meet for it to actually work. Like if I make this 3 and I make that 4, I could make that 5. And that works because 3 plus 4 is greater than 5. The sum of the lengths of those two sides is greater than that one. So yes, that can make a triangle. But if I tried to make one and I had, let's say this side was 3, this side was 8, and that side was 2. Because 3 plus 2 is less than 8, there's no way that you can connect that to make a triangle. You'll end up having that big gap there. So the sum of the lengths, the smaller two, would always be greater than the third one. If it works, you can make a triangle. If not, it's not possible. So some examples of that. Example 3. Is it possible to form a triangle with side lengths of 2 centimeters, 2 centimeters, and 5 centimeters? So, what do we think? No is correct. Because if we look at 2 plus 2, that's only 4, which is less than 5. And it's only going to be a yes if when you add those, you get a number that's larger than the biggest one. So, try this one out. 4, 2, and 5. Do you think it's possible that if I had some string or some boards or whatever it be, and one was 4, one was 2, and one was 5, can I make a triangle? Correct answer is yes, because 4 plus 2 is 6, which is greater than 5, so yes, those could be connected. So one more set. 3, 2, and 5. 3, 2, and 5. No is correct, because if you add 3 plus 2, that equals 5. And our previous theorem said it had to be greater. Less doesn't work, equal doesn't work. So the only time you're going to be able to say yes on these is like this middle one. If your number plus your number is greater than that third side, then yes, it'll work out. If it's less or if it's equal, you'll say no. When your assignment asks you for an explanation, the work that we showed here would be the explanation. You just show me that, okay, these two together, that's less, that's why I'm saying no. These two together is greater, that's why I'm saying yes. These two together is equal, that's why I'm saying no. Example 4. A triangle has one side of 10 centimeters and another of 14 centimeters. Describe the possible lengths of the third side. So I have some triangle. I don't really know exactly what it looks like, but I do know that I want this to be 14, and I want this to be 10. And I'm coming up with what on earth could I use for that third side. And that can vary quite a bit, because we don't know how long that is. I could take this side and kind of push it down. So maybe I'm dealing with this one, where that's 10 centimeters, and that's the side I'm looking for now. Or maybe I'm widening it up a little bit, making it an obtuse triangle. So we're going to have a range of sides. So what I would start with is x, and we want x to be less than something, and we also want x to be greater than something. To figure out what it can't be as far as the number on the lower bound, you can just subtract the two numbers you have. Because if you do 14 minus 10, you get 4. Our triangle can't have that third side being 4, because 10 plus 4 is 14. It can't be equal. So if I write it this way, I'm saying x is greater than 4. So 4.5 would be valid, and that would work. And then the upper bound, you can add them together. 10 plus 14 is 24, which wouldn't work because they're supposed to be equal. But as long as we use something that's less than 24, like 23.9, that would work. So this is the answer. And I want you to write it in that form. Your lower bound is less than x, which is less than your upper bound. And to find that lower, you can subtract. To find that upper, you can add. And that is lesson 5.1 and 5.3.